Okay. Wow. This is already over 7 centimeter. And this is, yeah, this is about 2 centimeters. So the numerator is pretty correct. And this is over 7 centimeter. And the 2 centimeter diameter is 1. So I have to 1.5 plus 1.7, that is a 3.2. And this is over 7. So that I have to estimate at least more than 10 centimeter. Oh yeah. $11, maybe 12. The more the better, right? The solution will get close. So I increase the factor of what? So it will be reduced to the frequency that is less than 1 kilohertz, but is very far from what we experimentally observed. So this is what really happened when we designed the resonator. Not easy, not accurately estimate the resonator's frequency, and it only roughly estimate the resonator frequency using this formula. Okay? So what we usually do is we estimate resonator's resonance frequency using that formula and then tune it. That is what actually happened in automobile industry. For example, in automobile industry, when they found some whistling noise coming from the, for example, intake system, okay? Then what you have to do? You have to put the sound barrier, because noise is coming over here. For example, 1 kilohertz. Okay? You take the air from outside to burn your fuel intake system, but you found that there is some whistling noise. How the whistling noise is coming from inside. Then what you want to do? You want to put some sound barrier over here to block the frequency of 1 kilohertz noise coming from the inside of the car. And what you can do, if you block it, your engine will stop it. Right? So you cannot block it. And how can you block it? Block means you put impedance mismatch over there. And what would be the alternative way to put the impedance mismatch? Resonator, put the resonator. If you put the resonator over here, if you put the resonator over here, and what happened at this cross-section? The cross-section, at those cross-section, fluid particle velocity is infinity. Therefore, there is an abrupt impedance mismatch at that point. That exactly same as I put the wall over there. Because wall in acoustic terminology means wall produce impedance mismatch, right? Wall is no longer wall. Wall is impedance, the element of impedance mismatch. So by putting resonator over here, at this frequency, 1 kilohertz, if the resonator has a 1 kilohertz sound, then what happens is they build up big impedance mismatch at that area or position that will block the sound coming from the inside of the engine. Okay? So that's why we use the resonator. Resonator does not take the sound inside. Some people explain that way. Resonator is like 물 먹는 하마. Sorry. There is a product in Korea that is called the eating the hippo. Hippo. You see? Huh? Drink water. All right? So the resonator is not sort of a hippo observing sound. The resonator is just a device to provide abrupt impedance mismatch in space. Okay? So now I suggest you think about every discontinuity as the impedance mismatch. Using that idea, we can build up invisible wall in the space. If you make impedance mismatch in space, suppose you build an impedance mismatch over here, then you cannot hear my voice because there is an impedance mismatch, therefore my sound coming from this side all reflected. Okay? Suppose you put the series of resonator inside of the duct, then what will happen? There is many impedance mismatch that dedicated to each frequency, therefore it behaves as like a filter, tuned filter. Okay? But as we demonstrate by using this case, it's not easy to accurately estimate the natural frequency. So what we normally do is we roughly estimate the natural frequency and tune it. How to tune it? Change the volume. Fill the water, for example. Right? And we can tune it. Not that simple. Actual industry. And it is not desirable to put this kind of bottle in a car, right? If you see this kind of bottle inside of a car, it looks ugly, and it's not good to have a long life because problem over here. So what you usually can see is something this kind that has a small hole over here. It has a pipe. Another conical type pipe surrounds the pipe, but that pipe has a small hole inside, and that has a volume V and neck length, effective length, and that provides abrupt change of impedance in a pipe that blocks the sound coming from intake. Okay. So that's what happened in acoustically small space. And next, what if I have this kind of chamber? Okay? This cross-section can be considered as acoustically small space because compared with the wavelengths, cross-sectional dimension is very small. But this length is very large compared with the wavelengths, so we have mixed dimension, mixed dimension. One is acoustically small space and the other one is acoustically large. What happened is there will be some wave propagating in this direction, but wave is a standing wave in this direction. Okay? There is a standing wave in this direction and propagating wave in this direction. But when we go through here, the standing wave in this direction would be, the wavelengths in this direction would be much larger than this.